Hello students, this is lecture 19 of MTH 201. In the last lecture we studied arc length and curvature of of a, of a curve, right? Okay. So today we are going to begin an important section of this course which is known as Riemann integration. So there are two kinds of integrals that we'll talk about, double integral and triple integral, depending upon the definition of the function. So let us start with a recap on what you have seen in MTH 101. Okay. So let f going from closed interval AB to R be a non-negative bounded function. The curve in the figure represents the graph of f. So this blue curve that you see is the graph of f in this case. The integral a to b fx dx is the area of the region under this curve, right? So this is something that you already know. And what is this region? It's x comma y in R2, where x varies from a to b and y varies from 0 to fx. Okay, so x goes from here to here and y goes from 0 to wherever the curve ends, right, which is fx. So how do you compute this integral? The integral is approximated by the sum of areas of the rectangles as shown. So you draw rectangles, uh, a large number of rectangles which approximate this area, and you let these rectangles basically become larger and larger. Now if the summation I going from 1 to n fxi star xi minus 1. So what is this quantity? This quantity is nothing but area of a particular rectangle, right? So if I look at this interval, this rectangle, okay, so here xi minus 1, xi are the endpoints of these interval. Therefore, what is its length? It's xi minus 1. So that's the base of this rectangle. What is its height? Its height is fxi star, where xi star is this point in this interval. Okay. So if you look at this rectangle here, that's basically giving you this much area, right? And then in each subinterval you pick a point, like in the first one you pick x1 star, then x2 star, and so on, and then you add up all those areas, which is basically the area of this shaded region. Okay, there are, of course, it's not perfect, right? There are some extra terms here, extra value here, but then there is something less here and so on. But then what you do is, so if this sum converges, as maximum of xi minus 1 goes to 0, meaning that the base, the length of each subinterval, if it goes to 0, then obviously you need lots of rectangles, right? So if this goes to 0, then the number of intervals should go to infinity, and the sum does not depend on the choice of xi star. So if this converges as the lengths of intervals go to 0, and the sum does not depend on what point you pick in the subinterval, then we say that f is integrable over interval AB, and the limit is called the integral of f over AB, and it's denoted as this, right? And here in this particular notation, x naught is A and xn is B. Okay. And this is a major result, that if you have a continuous function on closed interval AB, then it is integrable over AB. Okay. So this holds true for a continuous function on AB. And also we know that if it is continuous on AB except for finitely many points on AB, then also it is integrable. That is also one of the results you should have seen in MTH 101. Okay. So now let us take inspiration from this and let us define what is known as double integral. Okay. So we are going to start with first integration over a rectangle. I'll explain what I mean by that. And we are going to focus on non-negative functions to start with. So let f goes from closed interval AB cross closed interval CD to R be a non-negative bounded function over the rectangle. So what is this notation? This notation will appear several times in this course. In fact, from now on you will see it a lot. So you should understand what this notation is. This means the collection of all the points x comma y in R2 such that x varies between a and b and y varies between c and d. Okay. So here you can see, if you look at the xy plane here, this r is basically the r we just spoke about, right? So the x coordinates go from a to b and y coordinate go from c to d. So that will give you a rectangle in the plane xy. Okay. And we wish to find the volume of the solid S in R3 above this rectangle and below the graph of the function, right? So it's a function of two variables and it's a non-negative function. So you can see that its graph is lying in the positive z-axis. So you look at this graph, you look at this solid, okay? So you can imagine that this is like a tent whose base is a rectangle and you're looking at this solid inside it, okay? And we wish to find its volume. What is this solid? It's again representation like before. It's collection of now points in R3, right? Because this is a solid in R3 where z goes from 0 to this height, which is fxy, and x and y vary over this rectangle, which means that x goes from a to b and y goes from c to d. Okay, so we want to find the volume of this solid. Now the idea is quite similar. So in one variable you had an interval as your domain and you divide your interval into subintervals. Now our domain of the function is a rectangle. So we will divide a rectangle into subrectangles. And how do we do that? So divide the rectangle R into smaller rectangles as follows. So divide the interval AB into M subintervals. So on this direction, you make M partitions. Okay. What is the length of each partition? It's B minus A by, this should be M, I'm sorry, M. And similarly, you divide this side interval CD into N subintervals and each one will have length D minus C by M. Okay. So I'll correct this M and N. They need to be switched. So you're dividing the interval into equal parts, both sides. So when you do that, you get a mesh-like structure which is as shown here. And this gives a decomposition of R into M times N subrectangles, right? Because in this side you have M, this side you have N. So total boxes will be how many? They will be Mn. And let us call them Rij, where I goes from 1 through N and J goes from 1 through M. Okay. And what is the area of each subrectangle? It's going to be equal and it's going to be delta x times delta y, right? Because this is how we have made the partition. So we obtain a grid or mesh-like structure as shown here. Okay. So now in each subrectangle, you pick a point. So let me call that point xij star, yij star. You pick any point. And then what you do is you look at the cuboid, or I should say, yeah, this is what you get, right? A cuboid. What is the base of this cuboid? It's this rectangle Rij. And what is the height of this cuboid? It's the value of the function at the chosen point, which is fx ij star by ij star. So what is the volume of this cuboid? It's fxij star by ij star times the area of this rectangle. What is the area of this rectangle? It's delta x delta y. Now you have found out what is the volume of this cuboid. So then you vary over I and j and you sum up the volumes of all the cuboids. So the volume of the box region with base Rij and height fxij star by ij star is given by product of the height times the area of the base, and we approximate the volume of the solid S by the sum of volumes of all the boxes with base Rij and height fxij star yij star as I and j vary. So the double integral of fxy over the rectangle R is defined as, this is the notation, we will explain it in a minute, and it is nothing but, now you want to let both m and n go to infinity, right? So both directions it should go to infinity. You sum over all the possible boxes that you get, and provided the limit exists and is independent of the choice of xij star yij star. Okay, so if this limit exists and it does not matter what point you pick, then you say that double integral exists. So the sum in the definition above is called a double Riemann sum. So of course, for a chosen point you will get a double Riemann sum. So as you change the point, you will get different Riemann sum. Now in the Riemann sum, we can evaluate f at any point in Rij, right? Because if this, so the definition is that if this does not matter, if it does not depend on the chosen point, then you say it is integrable. So therefore we can choose any point that we wish, right? If we know that function is integrable, then we should be able to pick any point, right? By definition. So in particular, we can take it to be the center of Rij or a point where f attains its maximum or minimum in Rij. Okay. Now let us come to this notation. So this double integral refers to function having two variables, a function of two variables. You write the domain on the bottom like you do in one variable. And what is this dA? So in one variable you write dx, dy, or whatever the variable is, right? So that is the infinitesimal change, right, in the variable. So what is dA? dA uh, is the infinitesimal area component, right? And it is also written as dx dy. Okay, so instead of dA, we could also write dx dy just to emphasize that both x and y are changing. And if the limit exists, we say that f is double Riemann integrable function. The double integral gives the volume of this solid, right, which we described earlier. So the procedure is the same. Rather than an interval in that case, now you have a product of intervals, right? You have a rectangle and you repeat the same kind of process. Okay. Now that was for non-negative functions, right? Now suppose you have any general function which can take both positive and negative values. Then it's no longer area under the curve, right? Because now your curve is no longer upstairs, meaning no longer above the xy plane. So what do you do in that case? The idea is pretty simple. So any function f from rectangle R to real numbers can be expressed as a difference of two non-negative functions. Okay. So that will be denoted by f plus and f minus. So For example, if I take f plus to be maximum of f and 0, which is also called the positive part of f, okay, and f minus to be maximum of negative f and 0, which is often called the negative part of f, then f can be written as f plus minus f minus. So I would like you to check that this is indeed true. So once you have done that, you define integral of f over the rectangle R as, you just split the integral. Okay, so you know how to compute integral, double integral for a non-negative function, right? So now f plus and f minus are both non-negative functions. You compute them and you take their difference, and that is how you define integral of f, double integral of f. So f is Riemann integrable over R if and only if both f plus and f minus are Riemann integrable over R. So this is important. So even when one of them are not Riemann integrable, you can't say that f is Riemann integrable. So your definition is that if both are Riemann integrable, then only f is Riemann integrable. Okay. Now, again we have a theorem like in one variable. If f is a continuous function over the rectangle R, then it is double Riemann integrable. And the idea of proof is similar to the case of functions of one variable. In fact, using the same idea, we can show that if a bounded function f has discontinuities along finitely many curves, then it is Riemann integrable. What was the analog result in one variable? That if your function is discontinuous at only finitely many points in the interval, then it is Riemann integrable. Here, you don't take finitely many points in the rectangle. You can do more. Instead of finitely many points, what you can do is you can take finitely many curves in the rectangle. If your function is discontinuous on those finitely many curves, it's okay. It's still Riemann integrable. Okay? Alright. So now let us look at some properties of double integrals. These can be proved quite similarly as in the case of one variable. So I'll skip all the proofs here. So if f and g are two functions which are Riemann integrable functions from a rectangle to real numbers, then if you write R as a union of two rectangles, R1 and R2, then the integral over R is same as integral over R1 plus integral over R2. So the integral splits. So I should have said disjoint intervals, so they don't overlap. Okay, so they are disjoint intervals. So I will, yeah, I'll correct it in the PDF. So if f is less than or equal to g for every x and y in R, then double integral over R f is less than or equal to double integral over R g. If f is constant on the entire rectangle, then double integral of f over R is nothing but k times, that constant times area of R. So here you, in this particular scenario, you actually get a cuboid, right? Your solid S that we described earlier is a cuboid. Now for a cuboid, you know what the volume is. It's area of the base times the height. Height is constant now, which is k. So that's what you get. Linearity, if alpha is a scalar and you look at the function f plus alpha times g, then integral of that is nothing but integral of f plus alpha times integral of g. Finally, if you take absolute value of integral of f, that's less than or equal to integral of absolute value of f. Okay, so all these properties, they had analogues in one variable, and now we are able to extend them to functions of two variables. Okay. So now comes a very important concept of how to compute integrals. Okay, well, you have a definition which says that you take a partition, you choose points, you compute the volumes, you add them, and you compute the limit. But it's not an easy process, right? For a general function, computing those limits, taking those sums is a tedious task. So in general, one has several methods that one can use to compute integrals, and using iterated integrals is one of them. Okay. So let f be a function defined over this rectangle capital R. Now let us fix x. Okay. So f is a function of two variables x and y. So you fix x in the interval ab and you vary y. So when I look at the function fxy where x is fixed, I can think of it as a function of y alone, which is defined over the rectangle, over the interval cd, right? Now we have a function of y alone, so we can integrate this function over cd, provided the limit exists, of course. Then you look at this integral, which is integral c to d of fxy dy, because I am integrating over y, x is fixed. So this integral will be a function of x, right? So I'll call it ax. So now ax is a function of x and x varies over the interval ab. So I can integrate ax function over the rectangle, over the interval ab, and this is the notation from MTH 101. Now this can be expanded as, now ax, you know what it is. So you plug in ax here. So you get this integral. So what is this integral now? You have this inside bracket which is a function of x, right? Because you have integrated over y. Once you have done that, you do integration over x. So how does one read this? You first start from inside and then move outside. So you integrate over y first and then x. The integral on the right is known as iterated integral, and it may or may not exist, right? We don't know. So even when the inside integral exists, we don't know if the outside integral would exist. Similarly, you do the other process. You fix y and you think of fxy as a function of x alone. But now x varies over ab. We can integrate it over ab provided the limit, provided the integral exists. And you write this integral where you are now integrating over x as by. Why is it a function of y? Because we have integrated over x, right? So x variable is gone. So it's just a function of y. And then you can integrate now this function capital B, right? Over CD, because y varies over CD. So now by can be replaced by this integral. This is what you get. So now how do you compute this? How do you think of this? You first compute the inside integral, which is over x, and then you get a function of y, and then you integrate it over y. This is another iterated integral. So in the case of functions of two variables, there are only two kinds of iterated integrals, which are both given here. In one case, you first integrate over y, then with respect to x. In the second one, you integrate first with respect to x and second with respect to y. And of course, these may or may not exist. So what are the questions at hand? First question is, are the two iterated integrals are always equal? If not, under what conditions are they equal? Second, if they are equal, then are they same as the double integral, which is integral of the function over R? What is Fubini's theorem? It's a very, very important and famous theorem in analysis. It says that if you have a function f over a rectangle, which is continuous function, then the double integral of f over r is equal to both the iterated integrals. So in other words, the iterated integrals are both equal and they give you the same value as the integral of the function. So this is quite a powerful result. We are not going to look at the proof of Fubini's theorem, but we are of course going to look at several examples. Now Fubini's theorem holds for more general functions other than continuous functions, but we are not going to talk about them in this course. Okay, so remember this result. If you have a continuous function on a rectangle, then both the iterated integrals are equal and they are same as the integral of the function. So let us look at geometrical interpretation of Fubini's theorem. Okay. So recall we defined this ax and by, right? What was ax? It was integrating f as a function of y. So then your integral is a function of x and similarly by. Now what is ax? What is ax? Ax is you fix x. So when you fix x, you are fixing a point in this direction, right? Between the interval AB. So let's say this is my point. So when this is my point, I vary y, right? I vary all the possible values of y and I'm integrating my function. So now this function is nothing but for a fixed value of x, right? So this c that you see here is basically fxy where x is fixed and y is varying, right? So what is ax? Ax is nothing but the area of this purple region. So it's like one variable, right? So ax represents the area of the region or slice obtained by intersecting a plane parallel to the yz plane. So what is this? That plane in this case? X equal to this constant, right? And the solid S, which was the entire solid, which was the solid that we were talking about in the beginning when we defined double integral. So AX is the area of this purple region. Similarly, what is so thus integral a to b ax is what? It's nothing but adding these areas as x varies of an interval. So you can imagine all these purple slices, right? As you vary x in this direction and you add them all up. So integral a to b ax dx is nothing but that. It's looking at the volume of the solid as a sum of the areas of these slices. Okay. Similarly for by. So by represents the area of the region obtained by intersecting a plane parallel to the xz plane and the solid, which is this purple thing, and then you vary over y. So this integral is nothing but adding the areas of these, and Fubini's theorem tells you that a volume of the solid is nothing but the sum over all these areas. So it doesn't matter whether you take cross section, which is as shown in the first figure, or cross sections as you see in the second figure. It doesn't matter. It gives you the same value provided function is continuous. Okay. So recall Fubini's theorem. So what is Fubini's theorem? Double integral is same as integrating ax or integrating by. So with the description of iterated integrals on the previous slide, Fubini's theorem says that the volume of the solid S can be computed either by adding areas of slices of S parallel to YZ plane, which is as shown in the left figure, or by adding the areas of the slices of S parallel to XZ plane, which is in the right figure. Okay, so it doesn't matter which way you sum up things. So that's the geometrical interpretation of Fubini's theorem. So let us look at this example. So compute double integral of this function x plus y square over the rectangle R, where R is 0, 1 cross 0, 1. So it's a square. Now since x plus y square is a continuous function on the rectangle, we can apply Fubini's theorem and compute the above double integral using iterated integrals. So therefore, I am going to pick one of the iterated integrals where you first integrate over x and then over y. So you can write it like this. Now first you compute the inside integral, which is this, and this is just from MTH 101. I'll not get into the details. And therefore, when you plug it in the first equation, you can replace this bracket term by half plus y square, and then you use one variable integration, right? So you get 5 by 6. Now note, we could have used the other iterated integral as well, right? Because Fubini's theorem tells you that doesn't matter. And the problem can be rephrased as follows. Now this function over rectangle is a non-negative function, right? So the question could also be rephrased as find the volume of volume under the, this off should not be there, find the volume of the solid under the graph of the function fxy x plus y square between the planes x equal to 0, x equal to 1, y equal to 0 and y equal to 1. So I would like you to plot this in R3 and see whether this is the same thing, right? This is the same formulation as we were talking about earlier. Now the question, one of the questions we asked was, are the iterated integrals equal? And they can't be, right? Because so when your function is continuous, then you know they are equal. So if you have to look for an example, it has to be for a discontinuous function. And this is the discontinuous function that I'm talking about. So when you take this function, it's a discontinuous function, you can check. And if you integrate it over the rectangle, both the iterated integrals exist, but they are not equal. And I would like you to check that. Okay, so this is an example where iterated integrals exist, but they are not equal. Okay, so what have we done so far? We defined double integral over rectangle for non-negative functions. We moved on to general functions over rectangle. But now let us say our domain is not a rectangle. What do we do? So far we defined double integral of a bounded function over a rectangular domain. Now we'll extend the notion of double integral over a general domain. So let D be a bounded subset of R2. We still need a bounded set. That is, so what is a bounded set of R2? That is, there exists a rectangle inside which you can put D. Okay. So there is a rectangle in which D lies. So there is a rectangle R such that D is contained in R, and let F be a function on D and its bounded function. So you define a new function on the rectangle R, okay, as follows. So define function f tilde on R as f tilde is equal to f when the point is in D. Remember, D is sitting inside R, and it's 0 otherwise. So you can imagine that you have a rectangle inside which D is sitting. So inside D, your function is same as f, but outside D and inside R, it's 0 everywhere. Okay, so that's how you define this function. So of course, if f is bounded, then f tilde should also be bounded, right? Because at other points you're defining it to be 0 anyway. And if f tilde is integrable over R, now f tilde is a bounded function on a rectangle. We already know the concept of integral there. So if f tilde is integrable over R, we define double integral of f over d as double integral of f over R. Okay, so I'm sorry, this should have been f and this should have been f tilde. So double integral of f over d is same as double integral of f tilde over R, right? F tilde is defined on R. Okay. Now since f tilde is 0 outside D, it does not matter which rectangle R we choose such that D is contained in R. Because if there is one rectangle R inside which D is lying, you can of course take many rectangles, right? Infinitely many rectangles which contain D. So if R prime is a rectangle such that D is sitting inside R and R is sitting inside R prime, then integral of f tilde, I'm sorry, this should have been f tilde, double integral over R of f tilde is same as double integral of f tilde over R prime, right? It doesn't matter the extra portion, right? Because in that extra portion anyway your function is 0. So doesn't matter which rectangle you pick. The definition is independent of the rectangle that you pick in which D is sitting. So we will stop here, and in the next lecture we will talk about integrals of functions of 3 variables. Okay, we'll talk about triple integrals. So let us stop.